So for 5 and 6, well, you're matching them, so you can match 3. It doesn't matter what x is on number 3, right? X is irrelevant, right? So which one does it only depend on the y value? 4. So that's definitely A, right? Or sorry, 3, not A, 3. And it's not erasing, but you know, whatever. It's cool. That's fine. Be cranky. Like this. Let's get rid of that. I don't know. No. Okay, so we did that one already. So y prime equals y minus x. So where is y prime going to be 0 on this one? When what? When y is equal to 0. Y prime equals 0 when x is equal to y. And is there one where that's the case? Yeah, it looks like it's right here, right? It's weirdly drawn, but it looks like it's there, right? So this one looks like it's going to be 4. And then the next one, how do you figure out the next one? Pick values and just test them, right? Pick values and test them. So what values did you check? Well, let's just check for 5 here. What values would be interesting here? We know y prime is going to be 0 when x is equal to y, but that's also true here, correct? What's going to be the difference, though? What's the difference between the two? Hold on, what? What'd you say? One is squared and one is cubed. That's correct. So you're going to get steeper things happening. Is that what you're pointing out? Ah, okay. So here, you're right. What's one thing you notice? So what did you say about positive and negative?
Well, a negative squared is positive. So, for, you know, if you go to, let's say, negative x.
So what quadrant should we look at?
Quadrant.
Let's go quadrant 3, right?
Yeah.
In quadrant 3, when you're in quadrant 3 here, so, excuse me, when you're in quadrant 3 in this one right here, both x and y are negative. They're both negative. So what do we do next with that?
So, the x and y values are negative. They're both the same. So, quadrants 1 and 3 should be exactly the same.
1 and 3 should be exactly the same. So quadrant 1 and 3, not 1 quadrant, yeah, 1 and 3 should be mirror. Well, that's what so should be symmetric across the origin. And so it's for exactly and 2, 4. You're absolutely right. This is a great observation. Very cool. And you'll notice that that's the case. Right. Yeah. Very cool field. Got it. So there's our slope field, which we have. That's very nice. We have this nice visual representation. Theoretically, given enough time, could you have generated the slope field just as nicely? Absolutely. You just plug in a whole bunch of grid points and just start drawing line segments of the proper slope. So given enough time, you can make this. So given a differential equation, you can find the specific value of the slope at each point you want, right? The question, though, is, you got to it immediately when we started this a couple days ago, finding the general solution. Is finding the general solution always easy? Sometimes it can be very, very hard, right? Some of the questions where they even give you the solution and you have to verify that it's the solution, verifying isn't always easy, right? So we need something extra here. We need something extra. So for example, let's say I told you had an initial condition of y0 equals 1. And we drew this yesterday. So let's say that's right, I don't know, right here. You end up with a solution that looks like this. Everybody's okay with that? And what do we know? What do we know y prime is at 0, 1? What's the derivative right there? 1. Yeah, because what's the derivative? If we draw the tangent line? Looks like the slope is going to be. The slope is what? The slope is 1 at 1. So visually, does that kind of match what we have? Absolutely. That visually matches what we have. So here's the thing. We're going to use those tangent lines, similar to how you've used them in the past, as approximations for the actual function itself. So the solution curve with the initial condition y0 equals 1 is that curvy red thing, right? Does that curvy path totally match the blue straight line? Say no. It does not, right? But what about if you zoom in really far right here? If you zoom in really close, it's a pretty good estimate. The point is, sometimes it's much easier to look at a simpler tangent line than it is the function itself. For example, are you always able to anti-differentiate to find the general solution to these differential equations? No. And sometimes an estimate is good enough. So what we're going to use is a method that's going to give us good estimates for numeric values of differential equations, for solutions of differential equations. So instead, I'll make this a little bigger so we can use it a few more times. So you're going to travel, let's say you travel, let's just mark off some distances here that are all the same. So we're going to travel to here, and then readjust, and then once we get to the next x value, so let's say the direction said to go this way, right there. But we're going to get to right here, and then we're going to adjust again. We're going to get to this value and adjust again. So our overall path is this, then that segment, then the one up there, and then the one up there. And yes, it does get worse and worse, but the idea is you adjust according to the slope field, and you end up with an approximation of the actual solution given an initial condition. This is very, similar in a way to how we estimated actual integrals. How did we, when we made our first Riemann sum, you made those rectangles and you added up 5 of them, and you got an estimate for the actual area. How did you make the Riemann sum more accurate? You took more rectangles, right? So how do you make this estimate more accurate? What do you mean more points?
Like
More what?
or less separation between.
Less separation between each reading. So more course corrections is another way to say it. One thing we're going to do, just like with Riemann sums, this distance is going to be the same as this distance. Why does that help? It makes the math a lot easier. Theoretically, do you have to take the same distance every single time? No, especially if you're taking smaller and smaller ones, right? But the idea is we want to make the math at least a little bit straightforward, right? Just a little bit straightforward. So here's the deal. If I give you an initial condition on this right here, let's say I gave you this right here. I said this, and the initial condition y0 is equal to 1. I could then ask you, what is, I don't know, y of 3? If you wanted the exact answer, what would you have to do to the initial differential equation? Solve it. You'd have to find the general solution, right? Then you plug in the initial condition, and then you plug in 3. And you get the exact answer. But what happens if you just can't integrate it? If you can't integrate it, you could take a tangent line and do a linearization, right? Which you did before. You did linearizations, right? This is the exact same thing, except what you're going to do is take a linearization, but before you get to the x value you want, you're going to course correct, course correct, course correct, course correct, course correct a number of times. So you're going to get questions that are going to say, here's a differential equation, here's an initial condition. Estimate some value using a step of like 0.1. So what does that mean? You're going to course correct every 0.1 until you get to your final estimated value. You can make some generalizations, like for example on this one, where does it look like your estimate is always going to be on this curve? Above or below the actual value? Looks like it's going to. So the concavity rules are still going to hold. If it's concave up, what's the definition of concave up? Your tangent lines are always going to be below. Exactly. So certain things still hold. This is the exact same thing as local linearization, except we're just going to make it better by repeatedly adjusting. Step is h. So this is a distance. That's your step right there. You're going over that much. So how do you get from x naught to x1? You add x1 is equal to x naught plus h. The generalized way of saying this is xn is equal to x sub n minus 1 plus. You're moving h every single time. So if the slope of the line is f of x naught y naught, how far up did you go? H times f x naught y naught. That's how far up you've gone. That's the distance from here to here. So given that diagram, we know that y1 is equal to y naught plus what? Yeah, plus what? What's y1 equal to? Y naught plus what? How far have we gone up? I just pointed it out to you. That's how far we've gone up. So what is it? No. This right here, that's y naught right there. Right? H times f of x naught, y naught. Exactly. So if we generalize this, what is yn equal to? That's not yh, it should be yn, I'm sorry. Yn is equal to y sub n minus 1 plus h times f of x sub comma. Now, this is pretty straightforward, but it is a completely recursive definition. In order to get y2, you need y1. In order to get y3, you need y2. So in order to get yn, you need yn minus 1, yn minus 2, yn minus 3, all the way back to y naught. So the point is it is recursive. It's a little bit annoying, but it's something that you can do to estimate solutions to differential equations given an initial value. So what initial value would they give you here? They would tell you this point right here. They would tell you what the value of what that point is, and you have to start right there. You have to fill in the chart carefully is all. And if you want to make it more accurate, you make your h value smaller and smaller and smaller. Thomas gets to the important question, how many should we do? So first of all, the first column of your chart is going to be the n value, and then it's going to be the xn value and the yn value. So let's start with, let's do 0, 1, and 2. So find me those missing values now. Do that now. So you're adding 0.142, and you end up with 1.2. Exactly. So you keep on adding on to this. You correct, you correct, you correct, you correct. Absolutely. So that